Hi, this is Dr. Liu. In this video, I will explain what the second law of thermodynamics means and also what is entropy. So, in one way to say the second law of thermodynamics is basically about heat transfer. So you can say that heat can only simultaneously transfer from a hot object to a cold object, but it cannot spontaneously transfer from a cold object to a hot object. We have seen in the previous video that if you apply mechanical work, you can have heat transferred not spontaneously with work done. You can have heat transferred from cold objects to hot objects. But without any work done, it doesn't happen just by itself. For example, say if a cold water somehow it just turns hot because the ambient, which is also cold, can transfer heat into the cool water, somehow raise its temperature above the ambient, which is not possible. So that's one way to say it. And another way to say it is about entropy, which is how heat transfers. So a bit more quantitative. So let's define what entropy is. So entropy is the amount of heat transferred over the temperature T at which it is transferred. And sometimes we actually use the small quantity of entropy change is equal to the small amount of heat transferred under a certain temperature. So that's a more generic term, that a small amount of increase or decrease of entropy. And the increase or decrease will depend on the heat transfer direction. So if you have heat transferred into a system, the delta Q is positive, then the system will increase entropy. And if heat is transferred out of the system, that system will decrease entropy. And if heat is transferred between objects in one system, then one object may decrease entropy and the other may increase entropy. The sum will be a different story. So let's take a look at this example. Let's see, where we have, say, let's draw a block here. So this is the high temperature, T high, low temperature, T low, and we can only have heat transferred in one way, but not the other, spontaneously. So what happens if you have, say, one system which has both T high and T low? So you could have, for example, hot water mixing with cold water, or an ice cube in a lunch bag. So the lunch bag will more or less be insulating the ice cube from the outside, but the lunch bag still is warmer than the ice cube. So there will be some heat transfer from the lunch bag to the ice cube. And we know it's only one way. Right? There's going to be a puddle of water in the lunch bag. So with this idea, if you think about increase of entropy at the high temperature source, whatever that is, when they're transferring heat, is going to be equal to this. If there's a Q1 quantity of heat transferred, the high temperature source loses that amount, so it's negative. And it's transferring out that amount of heat at the high temperature TH. And the increase of entropy at the low temperature source is it received this amount as positive, but it received this amount at the low temperature. All right, so we're imagining the ice cube. So the ice cube is fixed at 0 degrees C as it melts, right? So that's a good constant temperature, low temperature, and the bag has slightly higher temperature, just assuming there's some hot lunch inside, right? So if you look at this, the Q's are the same, and this is less than 0, this is greater than 0. So for heat transferring out of a system, out of an object, entropy decreases for heat transferring into an object, its entropy increases. But what about the system? The whole system, let's call this system's entropy. So that should be the entropy of the high plus the entropy of the low. So high temperature system loses entropy, low temperature system gains entropy, but if you add them together is minus Q1 over T high plus Q1 over T low. We don't have to care about how much heat is transferred. We also don't have to care about at what exact temperature, but we know that temperature high is greater than temperature low, so that 1 over temperature high is less than 1 over temperature low. Let me rewrite that high. Okay, so that means this negative quantity here is less in magnitude or absolute value than this positive quantity here. So if you have a negative and less quantity, positive and slightly more quantity, then the result is going to be greater than 0. So this delta system entropy, in this case of heat transfer, is greater than 0. And we're ignoring the fact that there could be any heat transfer into the environment. It's only between and among a system of objects. So this is another way to describe the second law of thermodynamics in a more generic way, that the entropy in an isolated system always increases, or it stays constant or always increases. It never goes negative. It never decreases if we have an isolated system. So the entropy always increases. And if that's the case, always increases, that actually means increases with time, right? So if you think about this, entropy could be a good way to describe which way things happen instead of energy. Because in energy conservation, for example, if you have an energy conservation of a pendulum, so let's see, energy conservation, let's have a pendulum here. And we let go of the pendulum, pendulum swings down, swings to the right, it swings back, back, and then back and forth, back and forth. So there's no way that this process will actually somehow indicate the flow of time. Does the time flow indicate that this pendulum bob swings from left to right? No, it doesn't, because sometimes swings from right to left, and some other time left to right. So energy conservation only tells you that, well, this energy in one form flows into another form without loss. It doesn't say that it just only flows from one form to this other form. It could also flow backwards, just like this pendulum, from gravitational potential energy of the height to kinetic energy of the moving pendulum bob, back to gravitational potential energy of the due to the height, and back and forth. So the energy flow doesn't really tell you which way time goes, such as if you say were to break a coffee mug, it doesn't unbreak itself, right? There's this definitive direction of time that there was an unbroken mug, and then later there was a broken mug. It doesn't go back, reassemble itself into the unbroken mug, right? So the the flow of time cannot really be described by energy conservation. But as we already saw that in an isolated system, the entropy always increases with time. So entropy is a way to describe system, which way things, especially the irreversible processes happen, such as breaking a mug, right? So the irreversible processes happens so that the system's entropy increases. So now we think about systems entropy. What exactly is entropy? is heat transferred at a temperature. Is not energy, because heat transfer is energy divided by temperature, is energy per temperature, or joule per Kelvin, joule per Kelvin. And this joule per Kelvin, what exactly does it do? And in the macroscopic scale, we only see that this is describing how much heat is transferred at a certain temperature, right? So in macroscopic, it's entropy is heat transfer at a temperature. In the more microscopic scale, and we can actually use entropy to describe um, randomness, or basically disordered. So what this means is, if you think about this example, say if you have two separate things, maybe two different color granules of sand. Okay, so which system is more random or disordered? The left one, where the sand particles are all mixed together, or the right one, when the sand particles are actually separate? Well, this one is more disordered or more random. This other one is more ordered. So it's less than random. So what happens if you take the more ordered system, say you shake it up, well, it becomes the less ordered system. And that's what happens in isolated system. The order always just degrees into less order, and less random becomes more random. So that is the direction of time, basically taking things from more ordered to less ordered. Okay, so the entropy basically describes the absolute value. The value describes how random a system is. And isolated systems always goes from less order, less random to more random, randomness.